Cool. All right. So welcome. This is hopefully not a too long presentation on the Jetson carrier. Jump in if you've got any questions at any point. Yeah, I guess we'll just fire away. So yeah, first off, just sort of an explanation of like the different layers of Jetson. We will refer to like all of these things as the Jetson, but they're distinct things. First off, on the left, we've got the carrier board. So this contains this connects to the module, which is in the middle there. And basically all it does is break out all the signals to different connectors, so like USB and Ethernet and stuff like that. Generates all the power rails it needs for the peripherals, and then have a couple of things like buttons and miscellaneous circuitry. And then we've also added a power over Ethernet stuff onto there as well, for the radio. So that's the carrier. So this is actually what we designed. And then what plugs into the carrier is the Jetson TX2 module, which has this 400 pin connector on it, which connects to this one here. And this has its own power rails as well. So you supply it with like 12 volts, and it will generate all the power rails it needs internally to run the processor, run the memory, all the IO for like USB as well. And it's also got 32 gigs of storage internally. And then finally, inside the Jetson TX2 module is the actual processor, which is the Tegra X2. This contains the GPU, the CPU. There's also another CPU, but I won't go into much detail on that, and stuff like the memory controller, a few other tiny things. But yeah, so there's sort of the three layers. Everything I'll be talking about is on the carrier board itself, but you do need to be aware of these different layers because particularly the naming schemes of things gets complicated later on. Cool. Any qualms about that? Sounds good. So this diagram down here, this is the blue box is the Jetson module, and then the green box is the Tegra X2 chip. So you can see there's stuff like the power subsystem, and there's like wireless and like Wi-Fi, and all the storage and stuff is here. And then all this stuff in red is what's on the Jetson carrier itself. Cool. All right. So biggest question of all, why? Why do we want to do this? Basically, the dev kit carrier is really big. It only has one USB port, or USB-A port, technically. It's got a lot of extra stuff on there, like camera serial interface and display serial interface and other stuff that we don't care about and we don't need. It doesn't really interface well with the rest of the Rover because you've got to connect onto these pin headers to get all the signals out of it. And because it's got right angle connectors, when it's inside the Rover body, it's really hard to plug stuff in. So we had all these like right angle adapters and stuff, which was a nightmare. So in response, we designed this one, which is much smaller. All the connectors are vertical, and everything gets broken out easily into the rest of the Rover, so we can plug stuff in much easier and access all those signals. Cool. Just a bit of stuff on the like information about the Jetson carrier when you're designing it or doing upgrades or whatever. This is on Euclino. There's basically like 3/4 key documents that you'll need. The Jetson datasheet here is about the module itself. There's not a lot of information that's like super useful, but you might find a couple of things in there that's useful. It's sort of more about like the specs of the Jetson module and how you interface, like, and what it can do basically. This Jetson OEM design guide is your Bible. This document is amazing. It has literally everything you need to design a carrier board for it, and so much nitty-gritty information. If you're stuck on something, chances are it's in there. And then lastly, there's the schematics. So these are the actual schematics for the PCB, for the carrier board. And there's two. So the B04 schematic, which we found like in some dusty corners of the internet, is an old version of the schematic. It's actually an old version of the carrier board. And the reason why they upgraded it is because they released the Jetson TX2i and the TX2 4GB, which have slightly different requirements, particularly around the power on circuitry. But because we don't use those, we can just use the one that's compatible with just the TX2. And there's a lot of stuff on the schematic that gets cut off when you switch back to the one that's only compatible with the TX2. So they're both there if you want to have a look. They're quite long, quite big, which here we are. So this is what the schematics kind of look like. I've only grabbed a couple of screenshots, but there's a few things that you'll want to be aware of when you're looking at them. First off, lots of components on the schematic say no stuff, which means it's not populated on the PCB, so you don't put it in. So where it said no stuff, we just didn't place it in our version of the schematic. So just be aware of that. There's a lot of stuff that there's huge chunks of circuitry that just get deleted when you actually look at what's no stuff and what's not. Other random thing that you might not be used to is they have all these weird power rail injection things on the top right of most of the sheets. You can just ignore these. They just they must pull the net onto that schematic page basically. When you're exploring the schematic, use Control F to see where nets go. They don't often, it's very hard to tell. They'll just go out to a port on a page, and then you're where the hell does it go? So you really got to use Control F to find where they actually connect to, and you really got to search through everything to make sure you've got everything when you're copying it across, or when you're making sure that you've got all the functionality intact. And lastly, there's a few circuits on there that we've just completely removed because we don't need them, which may come up later. Cool. Any questions on the schematics here, or this stuff, or why we did it?
Well, so the NVIDIA schematic is basically a PDF file.
Yeah, they're all PDFs.
Right,
so
yeah.
I should wait. At the end, I might show you what it looks like. Show you all the documents if we have time, just to give you some context. Cool. So now onto our schematic structure, which is a bit of a meme, to be honest, but it's good to understand what's happening. Yeah, so the top sheet's kind of stupid. The top sheet's the one down here. It's got this absolutely giant subsheet block in it, and 90% of it's not connected to anything. And this is what I mean when we say that we don't use a lot of the stuff. All of these pins are pins on the connector, and we literally don't connect them. All of this stuff with the red no DRC checks. So yeah, but we kind of break it out into each module. You can't read it because it's too small, but I think this is the UART one, and then this is USB here. So all the relevant USB wires get jumped from the connector block to the USB block. It's all very logical flow. So it's a bit silly because this schematic sheet is I think it's an A1 page that's vertical to fit it all in, but it works.
It is huge.
Yeah.
And we definitely, because we worked on it as multiple people,
yeah,
it resulted this naturally, because we could say, hey, just do this entire sheet from NVIDIA. Obviously, you end up building the entire central module pins. And then I think we attached even a few sub-modules and then deleted them later.
Maybe. Yeah, I can't remember. There was definitely things that we removed last minute because we didn't need it. Yeah, and this sheet down here, this is the actual connector, that 400 pin connector. So there's each of these blocks is one row of 50 pins. And then there's a bunch of grounds and no connects, and then all the ports that we break out to this block here. And then yeah, we've got all the different schematic sheets here with different nested levels for some of them. Cool. Any concerns?
Yeah, when you say this is a bit silly,
yeah,
is that it's a big connector, that's crazy, or is it that you would design the sheet structure differently?
To be honest, I don't think I would change how we do it. It's just a bit absurd that we have an A1 sized sheet as our main sheet in order to fit everything. It's because we went with this subblock structure. If you look at the NVIDIA schematics, they don't have any of this logical flow on how things are connected together. They just have a net label, and then it connects on page 47 to a different net label, and you just got to Control F and find it, which I really didn't like. So that's why we did it this way. Cool. All right. So this is the Jetson carrier with all of its glory, and this is what everything is. So well, what most of the things are. So this is that 400 pin connector, and all of the traces, pretty much everything spans out of this and connects to various things on the board. To start with, we've got all the input power stuff here. So this has stuff like checking that the power is stable before turning on, and also like reverse. I think it's got reverse voltage protection on it as well. So that all happens down here. These are the 3 buck converters. So the 1.8 volt, 3.3 volt, and 5 volt buck converters, which the power is used for all the peripherals. So yeah, steps down the 12 volt input to whatever voltage we want. Worth noting as well, the input power can actually be from, I think it's 9 to 19 volts. So we designed for the full range so that we could use the 12 volts in the Rover, but also the 19 volt power supply that comes with the Jetson. Couple of buttons like power on, SD card. This stuff here is the controller for the fan, which is on the Jetson module. HDMI stuff, 1 USB port with its like on load switch there, another USB port, another USB port, Ethernet here with a bit of LEDs and stuff, and then the power over Ethernet, like 24 volt boost converter here. And then all of this is just level shifting for all the different communication standards, and then also the CAN transceiver. The GPIO expander, which we'll come to in a bit, we probably don't need. And then finally, the RS485 circuitry here, which is basically defunct now. So yeah, I'll also go over that. Yeah, any confusion on this stuff? Good, cool.
I just wanted to add a couple comments.
Yeah, go.
Special things about this design is the buck converters were, at least by NVIDIA, rated for something like 7 amps each, which is kind of bonkers. And while yes, the specs for the Jetson carrier are 9 to 19 volts, there are a few circuits related to voltage stability that are designed specifically for 19 volts, which we then later found out and had to modify for 12 volts. So there's a little bit of analog wizardry in the voltage side,
Yeah,
and the outside.
it's very annoying. Anyway, yeah, no, good points.
I just wanted to ask Will, because I've forgotten, is the Jetson mainly 1.8 volts or 3.3 volts logic level? Because I've forgotten.
Like the processor.
Yeah, like because we've got a lot of level shifters. I can't remember what they shift to.
I think most of them come out at 1.8.
Yeah.
It's a mix though. It's a bit weird.
It is a bit weird.
So all that stuff's in the design guide.
Hmm.
Cool. A bit about general layout. So like why did we put the USB ports up here, and why did we put HDMI there and Ethernet there? The answer is it's the kind of layout across the board is completely constrained by the connector fan out. It's a nightmare. I've done this probably a dozen times over the course of making the board. And the main constraint is the differential pair fan out. And the reason for that is you can see all the differential pairs here. There's 2 traces fitting between each of those pins. I think is that a 1/2 mil pitch? I think.
I believe so, yes.
Yeah. So wait, no, that can't be right. No, it must be
One.
well, is it? It must be 1 mil pitch.
It's 1 mil and they're point.
No, that must be bigger than that.
0.4,
That's like
0.2
2 mil
traces.
pads. I think it. Anyway, it doesn't matter. Whatever the pitch is, it's very small, and you've got to fit the two traces for the differential pairs through it. So the differential pairs are used for USB, HDMI, Ethernet, and what's even worse is for HDMI, you have to get all 4 of the differential pairs out, not only in the right polarity of positive and negative, but in the right order of 0 to 3. So it's like a game of Rush Hour where you've got to like get all the traces to go through these blocks in the right direction and come out in the right order. And when it's all said and done, once you get them out, there's basically a fixed order that you can put all of the stuff in.
This is primarily because we're using a 4-layer board because that's what we can afford.
Yeah.
NVIDIA just use more layers and they've got micro vias, and this isn't a problem for them.
Yeah, but we're better than NVIDIA because we can do it on a 4-layer board.
Yeah.
So take that. Yeah, so yeah, you can see there's basically all the like really high-speed signals kind of like coalesce over here. And then there's just like a bunch of empty space here. This is all like the camera serial interface, I think, and a bunch of like ground vias here. And then there's a few other random signals over here. And then like the power in is this big bar here. Yeah, so if you can avoid it, don't redo this because you'll hate it, or at least take a photo of it before you do, so you know what to go back to if you need to. Cool, onto power. This is a not insignificant topic. This is the diagram in the schematic, actually. It's in the schematic for some reason, of how the power distribution works. I'm just going to go to the next slide because we cross out a bunch of stuff that we don't use. But basically, you can see here the DC jack coming in, which is the 19-volt input. And this goes to the buck converters. And these buck converters are in a cascade, like a waterfall. So when the Jetson module receives power that's stable, so the Jetson module is connected to the 19-volt input. When it receives power that's stable, it will output this signal called carrier power on. And that carrier power on turns on the first buck converter. And then when that buck converter's on, and it's stable, it turns on its P good, the power good signal, which then turns on the next buck converter. And the same thing happens and turns on the final buck converter. So yeah, and then, so that's basically how the power on sequence works. Then all of that gets distributed out to, you got display connector. So like, this is like HDMI, USB, oh no, that's HDMI. This is the, okay, this should be a cross on this as well. HDMI's here, SD card, and then there's some other random stuff here. But you can see up here, this is where the actual module is, and we get essentially the direct 19 volts from the input. And there's also this signal here, V in power bad, which we'll come back to later, which is our old friend. But yeah, you can also see there's a few load switches. So for example, USB, they have like a load switch. So if the USB line gets shorted, you won't, it'll current limit to 1 amp and then turn the port off if the current gets too high. Cool. And then yeah, finally, we've also added in a 24-volt boost converter, which boosts up from 12 volts to 24 for the radio. Any questions? Cool. All right. Here we go. So yeah, here's the buck converter sequencing. So yeah, one thing that's worth noting is that both of these, so the 5-volt and the 3.3-volt bucks are 7 amps, which is quite high. So we used quite specialized buck converters for that. But the 1.8-volt buck converter is only 2 amps. So we probably went a bit overboard with the buck for that. This is just talking about the sequencing that I talked about before. And yeah, with the final, it's not on the diagram, but when the final buck is on, it's connected to this reset out low line. So when reset out low gets pulled high, it turns the Jetson on properly. So it waits till all of the voltage rails are stable and then turns the Jetson on. Which means that, yeah, 1.8 volts must be good before the Jetson turns on. And because of that condition, 3.3 volts and 5 volts must also be good because they're in a chain reaction. Yep, so we currently use these LM25148 buck converters, which do like 10 amps at 5 volts, I think. This is probably overkill, particularly for the 2 amp 1.8 volt rail. They're also a bit annoying because they're QFN packages. So they're these chips down here. They're super tiny and annoying to solder. So it might be worth in a V2 finding alternative buck converters that are a bit less annoying, particularly the 1.8 volt one, as long as they still have the like enable pin and the P good signal and all of that stuff. Lastly, it's a bit nitty gritty, but this 3v3 sleep rail is on some of the schematics. It's essentially all it does is it turns off when the Jetson is asleep. We never use the sleep on the Jetson, so I'm not sure if it's actually important, but I don't know if we can remove it. So that could be something to look into as well, just to simplify the circuitry a little bit.
Conversely, there is also power rails labeled hot. I think there's a 5-volt hot, which is supposed to drive the fan, and they're supposed to always be on. Even
when it's asleep.
Yeah.
Yeah. Cool. All right, now for the fun one. This is kind of interesting. So NVIDIA have developed this thing called UPHY, Universal Physical Layout.
NVIDIA didn't make it.
Oh, they didn't? Okay.
Can't give them credit for this one.
Okay, never mind. We hate NVIDIA. And they basically, what it does is it means you can convert between so a single differential pair that does PCI Express. You can convert it to be USB or SATA or I think that's it actually. So USB like super speed, so like a USB 3 port speed. Now it's not as free as you think. There are significant constraints in the implementation on a TX2. And this is also confusing naming scheme number 1. And you'll see like just look at the PCI, look at how the PCIe lanes are numbered.
You will learn very quickly that NVIDIA cannot count to 6.
NVIDIA can't count. Like you'll by the end of it, you'll appreciate that numbers are not their forte. So yeah, here it's like, and this is another thing where the numbers change depending on which layer you're looking at. So if you're looking at the Tegra X2 chip versus the module versus the carrier board, all the names are different. So you can see this like module pin is called PCI Express 1, and then the Tegra lane is lane 0, and then it's number 20 in the carrier board. Just a nightmare. I don't know why it's like this. I wish that it wasn't, but it is. You just got to be aware of it.
Did you follow the same naming scheme for our carrier board?
I think we copied the module names where we could.
Right.
I can't quite remember actually. It may not be 100% consistent. I'm not sure.
So does that mean, like in this case, instead of using PCIe #2_0, you would use PEX1?
We use, yes, I think so. Yeah, it's the pin, it's the name. Everything's named by the module name, the pin names in the OEM design guide. But then sometimes the lanes, the like nets are different to the pins, because like for example, like here, what's an example? So like here, PEX RFU is the module pin out, but we use it as a USB port. So we kind of change things around. Anyway, let me explain what we actually do. So you can see the default configuration is number 2, and that has 4 lanes of PCI Express for the PCI Express connector, 1 lane of USB for the USB 3 connector, and then 1 lane of SATA, which goes to the M.2 slot on Jetson. We don't care about SATA. We don't care about PCI Express. So, but unfortunately, you can't remap the SATA one. It's always SATA, which is annoying. But we do remap 2 of the PCI Express lanes to USB super speed lanes, which means we get 3 USB 3 ports. There are these extra 2 lanes. These are currently not connected. If you so wished, you could probably break them out to a PCI Express slot if you wanted to, but we haven't basically. So it would be 2 single lane ports of PCI Express. Yeah, so yeah, that's unfortunately, even though there's 6 super speed, like the 6 UPHY lanes, there's no way to make 6 USB 3 ports, mainly because they don't let you, and because there's only 3 USB 2 lanes on the Jetson. Does that make sense? Anyone lost about that? But that's how we expanded on the 1 USB port.
So when you're flashing the Jetson, do you literally only have those 6 options to choose from?
Yes.
Yeah, practically.
Cool.
Sweet. All right. A bit about USB 2. So in the default mapping of the Jetson carrier, so like the dev kit, 1 USB lane goes to the normal USB port. Great. 1 USB lane goes to the micro USB port, which is horrible. And this is used. The Jetson can act like a slave when you're flashing it, so you can actually plug it in with a micro USB port like you would a phone, and then you like hold the reset button and stuff. Kind of annoying. You do kind of need it. Well, maybe anyway. And then 1 goes to the M.2 slot, which I didn't know that M.2 had USB lanes until I did this project. But anyway, so basically 2 of them get pissed away doing nothing. So we use them for good. instead of evil. So we've paired them up with, I think, yeah, here we go. So we've paired them up with one of the USB super speed lanes from each of those UPHY pins. And now we have 3 USB ports, basically. So like I was mentioning before, one of these ports, one of the USB 2 lanes is used for the slave flashing. So we've actually designed, in here, there's actually a USB switch. So you can toggle between, there's a pin header that will switch the USB port to going, the USB 2 lanes to going out to the micro USB port or going out to the USB A port. So if you do want to flash it in the Jetson carrier that we made, you can just by changing that. To be honest though, this may not be required because you can probably just put it back in the default, like the dev kit carrier, if you need to reflash it. But it is a nice thing to have. And yeah, like I was saying before, each USB port has this load switch here. So if there's a short or it needs to turn the power off to the USB port, it can. Cool. Does that, any concerns about that? Sweet. All right. Ethernet. So this is pretty like hodgepodge because there's just like a bunch of different circuits that we have to get through. Ethernet's pretty easy. There's the 4 differential pairs. You don't have to length match all the pairs because, well, you have to length match within a pair, so they have to be the same length. But the 4 pairs can be different lengths. The way you know you can do that is because you can cut your own Ethernet cables and make them weird lengths, and it still works. We've got, so we, like I said before, we've got this 24-volt boost converter, and all the data lines just run directly from the Jetson module to the Ethernet connector. But we have this special Ethernet connector that lets us inject 24 volts onto the power over Ethernet. This is you could do this without this special Ethernet port. It's got what's called integrated magnetics, and the magnetics is what does it's got like transformers in it that does the voltage stepping up.
It's sort of, correct me if I'm wrong, but it's not only integrated magnetics, but integrated magnetics with the correct like connections to do this PoE, yeah?
I think so.
Center taps, because they were quite hard to find.
It was very hard to find, yeah. So there was, and I think there was like on the original schematic, there was a set of magnetics and an Ethernet connector that were there, but the magnetics were out of stock or like weren't made anymore. And it was really hard. Actually, I think they were like some weird Chinese part and we couldn't get it.
Yeah. NVIDIA kind of cheated because they just had a lot of parts on the board, which they had bulk stock of, or could get inside deals on, and we couldn't do that. I mean, they didn't cheat, but you know. Yeah.
So yeah, it's a good way to do it. I think the connector is like $15 though or something. Like it's really expensive, but worth it in this case. But yeah, just don't waste them basically. The only note for like a future version for this stuff is potentially adding like an overcurrent protection on the boost converter, just because it could be bad if it got shorted.
Would you suggest for a revision that we just do PoE off board for simplicity, or
maybe it just increases the number of connections? That's all. Yeah. Anyway, and yeah, we just use like an off-the-shelf boost converter like module, so it makes things pretty easy. Cool. Over to UART. Now this is the king of terrible numbering systems, like absolute god emperor of terrible numbering systems. There are it looks like there are 8 UART interfaces on the Jetson. There aren't. They go up to 7, but 4, 5, and 6 don't exist. How do I explain this? Anyway, so if you just look at here, for example, UART 3 on the Tegra goes out to UART 1 on the module. UART 4 goes to 3, 4 goes to, and then that's for TX2 4 gig, so ignore this. UART 1 goes to 0 and UART 2 goes to 2. Hey, so yeah, it's cooked. We use the module numbers, so the pin numbers, not the Tegra numbers.
So these are the ones on the right, yeah.
Yeah, so the blue ones.
The blue ones, yeah.
Even then, it's not perfect. But yeah, let me just explain what they're all for. So UART 0, which is Tegra UART 1 and Schematic UART 0, is used for the debug console. So this is like when you boot up a Linux device and it's got all the text spilling down the screen, it will also be spitting that same text out, this UART interface. So you can, if you don't have a display, you can hook up a UART receiver onto this and read what's happening. So this is how we debugged a lot of things when we were first starting it up, because we couldn't get it to boot. UART 1, which is Tegra UART 3, can be used for anything. So this you can break out. UART 2 is Tegra UART 2 and Schematic UART 2. This originally goes to the M.2 slot and can also be used for anything. UART 3, do not use. So UART 3 is here. This is actually multiplexed with the Wi-Fi and Bluetooth stuff that's in the Jetson module itself. So you can't use it. Well, you can use it, but to use it, you have to turn off the Wi-Fi in the module, which we don't really want to do because the Wi-Fi is kind of handy. Like I said before, UART 4, 5, and 6 don't exist. And then UART 7, it's a bit of a weird one. UART 7, so you can see it's called UART 7 on the Tegra, and then it goes to reserved pins, Ram-code 1 strap, and then it gets broken out to UART 7 again. So what the hell's going on? As far as I can tell, this is used for a similar sort of debug thing, but for the boot and power management processor, which is that second little like processor that's inside the Tegra.
I actually did not know this.
I believe so. I found some stuff that suggested that. So yeah, Leigh, I think Leigh, you'll probably go into a bit more
I'll
detail.
probably get into this a little bit.
Yeah, in Leigh's own presentation at another date.
I wanted to add for future revisions, UART 2 would be great to actually have properly working. We made the mistake of routing it out to try and use it for like general purpose stuff, but it's surprisingly hard to disable the Linux console for some reason.
Do you mean UART 0?
I mean UART 0, yes.
Yeah.
But yeah, UART 1 is like the regular one that is already broken out on the dev kit.
Yeah, so it'd be good to just have this come out to like pin headers or something, so we could probe it, and then just break out 1 and 2, and 7 can go to headers as well, because I don't think you can actually use that.
No, you can't.
Yeah. So you only get 2 UART interfaces basically. Cool. So yeah, this is a fun one. So this is one of the things that prevented us booting the Jetson for a couple of days when we first got it done. On the current version of the board, we've got these bidirectional level shifters because all the UART that comes out of the Jetson is 1.8 volt, and we want it at 3.3 volt. But because we use bidirectional level shifters, these have integrated pull-ups. So it pulls all of them up to the corresponding voltage on whichever side. And for some reason, the UART 1 TX pin and UART 0 RTS pin, and I think these are Tegra numbers, I'm not 100% sure, are used for this thing called Ram-code strapping. Basically, if you pull them in any direction when you boot the Jetson, it may prevent it from booting because it sort of sends configuration about how the RAM is, like stuff about how the RAM's configured over these lines while it's booting. And if you pull it in weird directions, you'll corrupt that data and make it not boot. So these are not actually on the board at the moment. Because we had to remove them in order to get it to boot. So if you want to use these, you need to switch to unidirectional shifters that have high impedance inputs. And then the input won't affect what's on the line. And yeah, UART stuff's only in one direction anyway, so it doesn't really matter if they're only unidirectional.
Does that mean?
Yeah, go.
Does that mean that there's only 2 of those 4 UART interfaces that were on the previous slide?
Well, you only only 2 of these can actually get broken out to like be used for stuff, because this one's for debug and the others don't work. And I think of these 2, both of them have Ram-code pins, which means we can't use them. So basically, maybe one of them works.
So how do we do any UART?
At the moment, we basically can't.
You can definitely, you just buy like a non-bidirectional shifter and it will be fine.
Yeah.
That's what NVIDIA did. We just didn't know that.
Yeah, we just have to update the, we might be able to find a drop-in replacement. I'm a little doubtful. But otherwise we just need to update that part, which is a pretty easy fix. Yeah, similar SPI. SPI, we've never actually tested it. All this is just level shifters again from 1.8 volts to 3.3, but we hadn't had a reason to test it. One random note is that SPI2, so we've broken out 0 and 1. SPI2 originally went to the DSI, or display serial interface, and camera serial interface connectors. We didn't break it out. I don't really know why. Probably just thought 2 was enough. But looking at this, it sort of raised the question, do we even need SPI? Or do we want to break it out to like more CAN controllers to get like 4 or 5 CAN buses?
I was going to suggest UART chips.
That's good.
That might be easier.
Yeah. Anyway, so there's lots of options there. We don't really use SPI much for anything, so yeah, that's an option. But we can discuss that at a future date once we've figured out what we want to do. Same again, I2C. It's just a level shifter with some pull-ups and pull-downs. The schematic has a few extra pull-ups and pull-downs because we weren't sure what the Jetson was already doing. So some of them don't need to be populated. My main question on this one is, do we even need it? Maybe not. Depends what we want to do, really. Only note is that the IO expander on the carrier board uses I2C, which I think is the next slide.
We used I2C for the BNO, for the IMU sensor.
True, but we're not using that anymore.
I didn't know. Okay.
Well, with differential GPS, we won't be.
Right. Okay.
Oh, we might use it for ARC, actually. I don't know. Anyway.
It seems like a pretty handy thing, especially because we can just pipe it through all the Nova cards.
Yeah, no, I'm just raising hypotheticals if we want to simplify things. Cool. So the IO expander. So basically, this is just 18 GPIO pins that you like tell what to do using I2C. The only thing on the Jetson carrier that's hooked up to this is the fan disable pin and the 5-volt enable pin for the HDMI. It's a bit random. I don't think the fan disable pin is needed. And Leigh's investigating if we can remap the 5-volt enable pin to just one of the standard GPIO pins on the Jetson. I think is that possible, Leigh, do you think?
Yeah, I'm fairly sure we can. And I think there might even be a guide for it.
Cool.
It's kind of a weird chip because I think even on the original carrier, it didn't do that much either.
No, it only had these 2 things.
Yeah.
And I didn't even break out the other ones, I don't think. So
yeah. Oh, well. Yeah, it's a good question, though. Do we want GPIO at all?
Yeah, I mean, we could use them. Yeah, a good question. I'm sort of inclined to like get as much of have the Jetson just be like the communication hub and then do all of the actions elsewhere. But
yeah, I agree. Yeah.
Anyway. Yeah, so with a bit of mucking around in the reconfiguration, we can probably get rid of this completely, which would be a good thing. And I actually don't. Is this even populated on the board at the moment? I'm not sure.
Not sure.
Yeah.
I think so. I think we had to for HDMI.
True, of course. Yes. Yep. Speaking of, cool. So HDMI, if you compare our schematic to the schematic in the NVIDIA schematic, ours is a lot simpler, and it's because we found this chip, this one here, that does like all the hard stuff for us. So it has ESD protection diodes, it does the I2C level shifting, it does the load switch for 5 volts, and it's got the hot plug detect and the like CEC. CEC is like some weird like one wire communication protocol.
Like I2C, but
yeah, it's kind of whack. Anyway, so it does all that for us. Basically, there's a bit of extra stuff for hot plug detect up here that we have to leave, I think, but substantially simplified. And then there's these like weird resistors and beads ferrite beads down here that are connected with this MOSFET. And that turns off when, well, that turns on when the HDMI is on. I don't really understand what it's for, but it's there.
I think
What
it's
is a
like
bead?
termination resistance.
Yeah.
It's weird.
Ferrite beads basically like a very small inductor, basically.
Oh, right. Yeah.
So yeah, onto the problems with HDMI, of which there are many. You'll notice that we got struck by bad numbering once again, in that HDMI DPX TXD P0 gets mapped to DPX TX2. So 0 goes to 2, 1 goes to 1, 2 goes to 0, and clock goes to 3. So basically I didn't catch this. All that ends up meaning is that red is blue and blue is red on the display, which is kind of funny. And apparently you can remap it in software, Leigh was saying, or you could just fix the routing.
Supposedly, yeah.
Yeah, so anyway, there's a few other cursed things that we haven't quite figured out. If you plug in like a normal full-size display, it just doesn't work. In fact, I think, does it crash the Jetson? I think it does.
Yeah, it does. I have no idea why.
It's very odd. And when you but plugging in that little USB powered display in, if you're running off a power supply, like the Jetson power supply, plugging that in works fine. Plugging in a display, but when you have it in the Rover running at 12 volts, when you plug a display in, it also kills the Jetson. We believe it's related to this V in power bad low signal that I was talking about before, which I'll come to in detail in a minute. It's kind of horrible actually, but it raises my final point. Do we even need HDMI? And the answer is probably yes, because it helps a lot with debugging when you're trying to get everything soldered. But it's not something we use in the Rover, so potentially we could get rid of. Cool. Any questions on like HDMI or any of this? I kind of skipped over question time. All good. Cool. Hopefully it's like being absorbed and not just going completely over your heads. Onto the SD card. This one's a bit of a meme as well. We haven't tested this, and the main reason is that this is how the SD card slot opens. I didn't know until I bought it. And the first step is that it slides this way, and when you slide it this way, it hits this capacitor and shorts the capacitor to ground, which is not great. So we just don't use it. You can like turn it off, put an SD card in, and then turn it back on again, but just figured it's easier not to worry. We've never tried it. We probably should. It wouldn't be that hard to try it.
I think I have tried it.
Okay.
I'll have to dig through my notes to know if it worked or not. I think it did.
I have a vague, yeah, maybe it did.
But at the time, software team like really wanted it, and they never used it.
Yeah. So yeah, the Jetson's got 32 gigs on board, which is like probably enough. And also like you can't really install stuff on the SD card. So, well, maybe you can. I don't know. But anyway, originally this was a full-size SD card on the Jetson carrier, so we made it mini to save space. Sorry?
I was gonna say, like, how's it actually connected? Like, what kind of protocol communication?
SDs, it's weird. It's got its own like weird thing.
It's a bit more like SPI.
Yeah,
Yeah.
Basically you just like wire it. You just like connect the dots. It's not that tricky. You just
like
map
chugs
them.
the bytes out in parallel, doesn't it?
Yeah. So
Lines.
yeah, you have to like length match the lines a little bit. But yeah, basically like the pinout of the Jetson exactly corresponds to the pinout of an SD card slot. So you just map them together and that's it. You can see like we've got like these little ESD diode arrays here to prevent high voltage on there. Haha, okay. V in power bad L. Here we go. This is a cruel mistress that we don't really understand what's going on. So this V in power bad L signal, it keeps what its purpose, it serves two purposes. The first is when you first plug power into the Jetson and it's charging the capacitors up, it's essentially like a derivative trigger. So if the voltage is rising, it will keep the Jetson powered off until the voltage is stable. And then when it's stable, it will send the signal. It will pull this low, and then the Jetson can turn on. And that happens, I'm pretty sure that happens before all the buck converters turn on. So yeah, basically it's so that it doesn't boot up prematurely. This is in the OEM design guide and like plastered everywhere. We don't really understand why exactly, but presumably it doesn't boot up properly if it doesn't, if you don't do it correctly. There's these two circuits. This is the one, this is the derivative filter thing. So it's got this capacitor here that like charges up when the power is rising. I won't really explain how this works, but if you put it in LT Spice, it does work. And then there's also this other circuit here, which basically when you turn off the power to the module, it will assert this flag and tell the Jetson to shut down before the power runs out, basically. So there's two. There's one for power up and one for power down. This is the one that's causing us grief, I'm pretty sure. And basically what's happening is that there's two problems. One, when we plug in high power USB devices, so before we tweak some things, when we plugged in the autonomous cameras, it would crash the Jetson. And it still happens sometimes if you have like a lot of devices on a USB hub and you plug the USB hub into the Jetson, it can turn it off. So that's what's caused some reboots at field tests sometimes. We fixed the problem with the autonomous cameras by tweaking some capacitance values like around, I think it's around here, like this one, 201 and 49. Because these are like an RC circuit and there's some weird like time constant stuff going on. We bodged this fix to get that to work, but we really still don't understand the underlying cause of why plugging in USB devices causes this to happen. They're not connected. It doesn't make any sense. It's super bizarre.
I was quite fond of the theory of it being kind of a noise issue,
yeah,
or potentially a temperature issue, because I've seen temperature issues before. I've got a video of this happening on the oscilloscope, which I could show you. It's not that interesting, but basically during a high current situation, the flag would get triggered really quickly for some strange reason. But then even, I don't know if it still happens post Bodge, but it would sort of slowly rise. I was just like picking up noise and going and going and going, and then I hit this sort of critical threshold and go whoop, and then turn off the Jetson.
Yeah.
It was kind of a crazy one. In the future, maybe this circuit should just not be analog, and we just buy like a voltage monitor type chip.
It's probably a good idea. That's a good thought. Yeah. What was I gonna say? But yeah, it's definitely needed. Unfortunately, you can't omit it. Yeah, and yeah, like I was saying before, we believe this issue is what's causing HDMI weirdness with the big displays and the small display, but we're not really sure. But yeah, if you want to, you can check out the link on Euclino. There's some notes on our adventures with that problem. The fact that there's a 0 ohm jumper here really makes me want to just pull it off though.
Yeah, exactly right.
So I don't know, maybe you can. We like on all the forum posts and stuff where people ask about this, they'll just say, like the people from NVIDIA will just say, you need it. And you're like, okay, but what happens if I don't? And it's like, no, you need it. It's like, okay, thanks. So who knows? I don't think it would kill it, but you might get like memory corruption problems. So anyway. I think we're nearing the end. Discharge, this is just a weird thing. All of the voltage rails are tied through these MOSFETs to ground. And when a Jetson turns off, it asserts this discharge wire, which just drains all the current, all the charge out of the capacitors, basically. That's all it does. So again, probably not really needed, but like good.
There is a lot of capacitance on board,
yeah,
just to sustain the really quick peaks of current.
Yeah,
I think they have to put it in for compliance reason.
Yeah, yeah.
Oh, yeah.
How is this not just shorting your power rails to ground?
Because discharge normally is pulled to ground, so the MOSFET's off.
it is shorting the power rails to ground, but they're not. There's no power input anymore.
Yeah, so it's
just
after you
the capacitors, just once.
Yeah.
Right. So how does it know that there's no power input?
So the Jetson asserts the discharge line when it turns off. So it like finishes everything it's doing and then asserts the discharge line, turns itself off, and then the discharge line will stay high until everything else is drained, basically.
Right. So it's draining itself, and then once all these power rails have discharged enough, then the discharge line has no power, so it turns off.
Basically, so technically the voltage that supplies the discharge line is from the internal supplies on the Jetson module, which have a different discharge thing, presumably, but we don't actually know what goes on inside it. So, yeah. All right, RS-5, we're now doing a different implementation, so this whole thing can go. Originally, we had trying to talk with the UART interface on the Jetson. This doesn't work, so we have this like connector here so we can inject it, but we're probably going to get rid of that as well.
An SPI to RS-5 chip might be interesting.
Oh, that could be interesting.
Not sure.
Anyway, yeah. The fan, this is just like a really annoying thing. On the schematics, there's this 5-volt sleep rail that is used in 2 places, the fan and the SATA connector. And the actual definition of this net is on the SATA connector page. And because we removed the SATA connector, we removed that definition. So this 5-volt sleep rail is not connected to anything. So we've got a Bodge wire on the back of the Jetson that connects this to the other 5-volt rail. So if you're going to redo it, we just need to fix that, and then it's good. A bit of stuff. This was requested by Matt. A bit of stuff about the differential signaling and like how you size it. So the Ethernet port, the USB port, and HDMI all use high-speed differential signaling, but they're all different. So different impedances, different like skews and stuff like that. So it's important that each wire in a pair is the same length within tolerance. It's important that each pair has the right trace width and trace gap to give you the right impedances. And for HDMI, it's important that all 4 pairs are the same length within a bigger tolerance. So you've got to match plus and minus, and then you've got to match 0 to 3 as well. All this information is in the OEM design guide on what they need to be. So as an example, I think this is USB. The termination resistor is 90 ohms. I believe that's done inside the Jetson module. And then the trace impedance, they give you like a differential pair impedance as well as a single-ended impedance. I think we have notes on Euclino about the difference and how you measure it.
Yeah, there is a page about it. Basically, it's differential pairs between the 2, and single-ended is from 1 through to the ground.
Yeah. So yeah, and then these values define your trace width and your trace gap. So how fat your trace is and the gap between them. And then here is I think this is the HDMI one, the maximum within pair skew. So you can have 0.15 millimeters difference in length across the entire trace, which is not a lot, or 1 picosecond if you prefer. And the difference in each pair. So, oh, sorry, no, that's not true. I think this is USB actually. And then the differential pair uncoupled length. So basically like how far you can have them travel without being like right next to each other is 6 millimeters. But in practice, I think these were basically 0 for all of ours because we did it really well. And I should mention for HDMI, there's another thing here for inter-pair skew. And that defines the difference in length you need to have between the pairs. In Altium, you can define them in the design rules. So we have these different classes of differential pairs. So this one here is a 50 ohm single end impedance and 90 ohm differential impedance versus 60 and 100. And you can see here, this one applies to the USB 3 lines, the HDMI lines, and the Ethernet lines. So you can define it all in the design rules and then apply them to the nets that are relevant. And then when you're actually routing the board, there's 2 different tools. There's the length tuning, which I don't have an example of it here actually, but when you're tuning the difference in length between the two wires in a pair, you use that, and it basically just gives you like a little slider that you can pull up and down, and it tells you like what the difference in length is. So you just like increase or decrease until it's correct. And then my favorite tool is the interactive differential pair length tuning. So this lets you adjust the lengths of all of your, so these are the HDMI traces here. So you can adjust the lengths of all of them to make them exactly the same length. So you get these nice little snaky wiggles. So these traces from these pads here all the way down to the Jetson connector within that fan out I showed earlier are at exactly the same length to within, I think it's like a 1/100th of a millimeter or something. Obviously there's like manufacturing tolerance on that, but they're as close as I can get them.
Just wanted to add two things on this.
Yep.
One is I'm fairly sure Altium calculates the thicknesses and widths for you when you put in a impedance, or I think it goes the other way around. Like you put in the things and then it will say, here's your estimated impedance. And that estimate impedance is based on your layer stack up.
True.
So in Altium, you say, here's how thick all the layers are going to be when you order it from GLC. And then it works out the impedances roughly. We were unable to get exactly within spec, but from reading the internet, apparently no one's able to get exactly within spec, and it doesn't matter. But we did have to buy a very specific stack up of 4-layer board from GLC. Now that's on the new cleaner.
That's right.
But it's just not something you want to forget, because otherwise it probably will not work so well.
Yeah, but the good news is we've had absolutely no problems with our differential pairs.
It's been crazy. I can't believe it.
So that was quite good to see, because it's something that like differential pair routing is like one of those voodoo magic
Really
things.
scary.
You get like plonked in, you're like, I don't know if this is going to work. And it did, so that's good. I think this is like probably the last couple of slides. Basically, we break out all of the useful stuff on this backplane connector on the back. And that plugs into the backplane. So this at the moment has CAN signals, RS485, UARTs. So these UARTs, like we've got UART 0 here, which we can't use because that's got the console log on it. UART 2 is here, but UART 1 isn't. I don't know why we didn't break that one out instead. Anyway, there's so many like tiny things on this board that are just like annoying. I2C, SPI. We broke out the GPIO pins. I think, do these come directly from the Jetson connector? I think so.
I think they do. Are they the ones they would CAN?
Yeah.
I think they are the 5-volt tolerant ones.
Ah, yes. Okay, cool. Yep. And then there's like a bunch of 5-volt stuff, battery voltage, and which we don't use. I don't know why it's actually connected here. I think I was originally going to use it for the boost converter, but didn't. And then this is this is also the backplane connector. These are just the like big bars in the middle here. So one's ground and one's it's labeled 19 volts, but it's actually the 12 volts from the backplane. Cool. A bit of stuff about assembly. This is the process. The 400 pin Samtec connector has lead-free solder charges on the pins. So you need to use lead-free paste with it and use a stencil, because otherwise you'll never get it right. We were very afraid that this wouldn't work, but using the reflow oven, we've had 2 for 2 successes on soldering this so far.
It was still a nightmare even with a stencil.
Yeah, we got better at it as we went, but yeah, stenciling's pretty hard sometimes. But yeah, once you, so the way we do it is we just paste the connector with lead-free paste, place the connector and put that in the oven to solder that. And then you sit there with a multimeter and check for shorts between all the pins and check that all the pins are soldered correctly by continuity probing to like where they should go, which takes forever, but it's worth doing, because if you have a problem later on, you're not going to be able to tell. So once the connector's on, then we paste. So we've got, I should get a picture of it. We've got a stencil that has a rectangular cutout that slots over where the connector goes. And then we pasted all the other components and placed those and then soldered it.
With the connector, if
Yep.
it doesn't work, how do you go and fix it? Like if one of the pins on the inside is not connected properly?
You can't. you try again, which is
You
why we have
could
like
try reheating it, maybe.
the problem is because of the solder charges. Once it's reflowed once, the actual distance between the pins and the it's hard to explain. There's a video online. If you look up Samtec C-Ray solder charge reflow or something like that, it'll show you how it works, and you'll understand that like it's really a one and done thing. If you don't get it right on the first go, you're just never going to get it again.
So then what do you do?
You take it off and try again with a fresh one. Yeah, but we haven't had to do that yet. We were warned. Oh, sorry, go.
I saw there was one document that you had when you went through these 400 pins.
Yeah.
And it was like an Excel thing. You'd labeled them green and yellow and so on.
Yeah.
I understood from that all the yellow ones weren't connected or had some issue with it.
No, so the yellow ones are pins that aren't connected to anything on the Jetson carrier, so there's nowhere to probe where they go. So they might not be connected, but I assume they are, and it's just there's no way to probe for continuity for them because like they're not connected to anything.
But also, I'm guessing we don't care about those.
We don't
if
also
they're not connected.
exactly. We don't care.
Yeah. Okay, so it just happened that every pin worked perfectly.
Yeah, so either everything works perfectly, which when you visually inspect the front row of each connector on each side, all 50 pins on the front and back are connected. There are 6 more rows in there that you can't see, so it's a bit hard to know exactly, but yeah, it's I think they're all connected.
Are there any notes about stencil thickness for this one? Like how did we get in contact with people from CERN?
It was like a mate. It's like a mate of Scott Wordley's or something.
Yeah, we like you emailed him like, how do we solder this damn thing? And he was like, just use your in-house PCB fab.
Yeah, use your paste printer. What? Yeah, there was a note on the thickness of this. Ultimately, I don't think it really mattered. I think he suggested that we use a thicker stencil, but the alternative and what was actually said in the data sheet of the connector was to use have your stencil pads be bigger, like your stencil apertures be bigger than the pads themselves, so that you get more paste per pad, basically, instead of using a thicker one. But yeah, so that's what we did, and it seemed to work. So that's good.
Cool.
It helped that we were like incredibly careful and like didn't do it until we had an absolutely perfect paste job. So,
you were meticulous. You had spent like a whole day on it.
I spent a whole day doing just this. Yeah, it was not good. Anyway, yeah, so we soldered all the SMD stuff on, and that includes the HDMI connector because the pins are SMD on that. And then before you get to have the fun and put all the through-hole stuff in, you've got to test all the buck converters because chances are they haven't soldered correctly. This is the QFN package for the buck converter, and it may look properly soldered, but I can tell you now that this pin and these 2 pins are not connected.
The chip's about the size of a fingernail.
Yeah, like your pinky fingernail. It's tiny. Yeah. So it's a real bastard. And I hate QFN really, but I'm getting better at it. But basically, yeah, before you turn it on, just have a look and see if you can spot anything. You can sort of see the little U-shaped crack between the pad and the IC. That is really the indicator that's not connected. So just check them all first, and then you can try power it on. So you supply 12 volts on the input, and then you need to supply 3.3 volts to carry power on to get the buck converters to turn on because of that enable P-good chain. And hope that the bucks work. It took us, I think the first time it took us about 3 days to get all the buck converters to work.
Absolutely, yeah.
So that was
we actually
holidays.
we still haven't finished the second board, so
true.
Anyone wants some practice?
Yeah. My only other note is that really do inspect it before you power it on, because if your buck isn't soldered correctly, there's a chance it can fail high and put 12 volts out on the output.
That's what happened with the second one.
Oh, is it? So
fairly sure, yeah.
Right. Okay. So like the which means that you, instead of getting 5 volts on your 5 volt rail, you get 12 volts, and then all your 5 volts electronics explode. So yeah, just be careful about that. It's very hard to tell, but it can happen.
Sorry for so much detail, but like, I hope this is in the new cleaner, but if it's not, like testing these, I had the current limit set to like 5 milliamps because at idle, it's only like a 3 milliamp draw. So if you go above that, they're not working.
I forgot about that. Yeah, really setting your current limit low will prevent, because if something starts to draw a lot of current, then it's going to drop the voltage massively. So if you've got a short somewhere, it won't kill stuff. Cool. I got lots of pretty pictures for this slide. Once the power is good, so you've got 3 buck converters and the reset line, you can actually measure the reset out line is going high. It should, yeah. That the reset outline is the line that tells the Jetson to turn on. So once you're at that point, and you're confident you don't have any shorts anywhere, then you can put your Jetson module in. And when you boot it up, it's unlikely that you'll get to the straight away you'll have display working. So you need to hook into the UART 0 line to tell. When we were testing it with Leigh, Leigh used his little digital signal analyzer to read it, but you could probably like hook it up to something like an Arduino or something, or like even an oscilloscope with a UART decoder.
Yeah.
Cool. And then once you're at that point, then you can put all your 3-hole stuff in. The reason we wait is because a lot of them are really expensive, particularly the Ethernet connector and the boost converter. They're really pricey. So yeah, it just saves you the hassle of having to desolder them later if you need to replace them or pull them off.
What is really pricey in this context?
I think the Ethernet connector is like $20 and the boost converter is like 25.
Well,
yeah, for a single component, it's like really expensive. So yeah, but it's good fun. And then once you've got that, this is like a picture from the day that we got the display working, which was a very fun day. So you can see here we're finally getting HDMI, and yeah, stuff you can read like what it's doing. EDID invalid, random stuff. And you can see there that's actually running Ubuntu there. So we got it going on. Did you do this slide, Leigh? Yeah, you must have.
Yeah, I did. Yeah. Oh, there's no text. You have to. I think my slides haven't saved or something.
Oh, wait, let me refresh it.
I've been adding stuff and they haven't been popping up.
There we go.
There we go.
Behold, yeah. So I think this is the fix for the VN power bad L that was triggering the.
That was mysteriously shutting things down when we had mysterious shutdowns for a while.
Yeah, so we just put another capacitor on top to double it.
And the bodge on the right, the resistor at that right angle at the top is actually soldered to a via.
Yeah.
Right underneath it. And that was like essential. I can't remember what it does.
It was the
signal. The P good signal or something.
Yeah, something like that.
Yeah, I'm sorry, Min. I have photos. They're just stuck in the cloud. There's another photo on the next slide of Will doing soldering
with the
microscope.
Yeah, look how big that syringe looks.
Yeah.
Yeah, and then to be soon, Leigh will be doing a presentation on all the sort of software-y, Linux-y, device tree, kernel-y stuff.
Yeah.
And how to remap the USB stuff and what the heck a jetpack is. So
yeah, so any questions you think of or have thought of, send me a message. I've been writing some stuff down just now. Yeah.
Sweet. Now there's definitely stuff we missed. I know, for example, that there's like a 10K pull-up on the pads there for the for like one of the P good signals because it was pulling up to the wrong voltage or something. anyway, so yeah, there's a bunch of like tiny stuff, but that should cover most of it. All of those bodges are listed in your Clino. So when if you're doing a V2 of the Jetson carrier, you can go through those and update the schematics. But yeah, hope that was interesting. Hope it made some sense, and can be a useful resource for Nova people to come after us. I'm glad that we have this somewhere so that so I can brain dump it somewhere and then have to worry about it being lost. But yeah, any final questions or anything?
Yeah, what was that last bodge on the right? Where it looked like there was the resistor and capacitor soldered together.
Yeah.
Is that intentional?
Yeah. So I can't remember what it I can't remember what it was. I'm pretty sure this is ground.
I think so.
Yeah. Basically we just had to have,
I'm looking in Nucleino now.
I think it was was it a pull down?
Yeah. We were pretty meticulous about documenting these bodges because we knew that we would forget.
Yeah, basically, so there's this trace goes out to a via under here, and one side of the resistor is soldered to the via itself.
Yeah, this resistor was really important because we changed the bucks from what NVIDIA did. So this resistor is on the carrier power on signal, which goes into the bucks in that chain. And this resistor pulls that signal down to ground so it's not floating. But the bucks we use have high impedance inputs, which meant it pretty much just kind of floats on or off randomly with the noise in the room or your finger.
Yeah.
Without this resistor.
Wasn't there a time where literally like when we touched it, it turned on or something like that?
Yeah. Crazy.
It was like really cursed. So
you just happen to find like a little space on the board for that.
Yeah.
For that resistor.
Yeah. There was just a convenient spot where like the voltage rail was near a ground, and we're like, oh yeah, we'll solder it there.
Yep.
So yeah, welcome to the art of bodging. There's also there's no picture, but on the back, there's a tiny wire that's like,
actually I put that in on that slide.
Oh, if I refresh it.
Yeah.
Let me refresh the page completely.
Hopefully it went in.
Nope.
Sorry.
Doesn't matter. Yeah, there's a tiny wire, like I was talking about before, to connect the 5 volts to that fan circuit because the net wasn't connected. Not that the fan is really that important, but yeah, gotta make sure we gotta take the little wins when everything else is broken. Alrighty, well, any final things? I might wrap it up there. Cool. Alrighty.